everyone. This next talk, we'll have Jiaqing Jiang tell us from Caltech tell us about the local Hamiltonian problem with succinct ground state as MA complete. So, Jiaqing.
Okay, thank you. Thank you for everyone attending my talk. So I'm Jiang from Caltech. I'm mainly working on the Hamiltonian problem. And today I'm going to talk about the complexity result on this topic. So I will first give some definition, and then I will talking about stating and results and some potential implications. So let's begin. So the key concept in this talk is local Hamiltonian. So what is local Hamiltonian? Intuitively, local Hamiltonian is just some kind of math model for locally interacting many-body systems. So for example, you can use local Hamiltonian to model molecules with many interacting electrons. And the concept of local Hamiltonian comes from chemistry and physics, where people study electron structure and interacting particles. So this is where local Hamiltonian problem comes from. And mathematically, local Hamiltonian is just it's just an n-qubit Hermitian matrix, which can be written as a sum of local terms. And here, local means every subterm only acts on constant qubits. So, for example, you can define a local Hamiltonian on a 2D lattice, where on each vertex there is a qubit, and on each edge there is a Hermitian term. And this Hermitian term only acts on the 2 qubits of this edge. So this is an example of local Hamiltonian. And in this talk, we mainly focus on estimating the ground energy, which is the minimum eigenvalue of H. And in particular, the key problem in this talk is called local Hamiltonian problem, which is a decision version of the ground energy estimation problem. So in this problem, we are given H and two parameters A, B, and we wish to decide whether the energy is lower than A or greater than B. So this will be the key question in this talk. And for this kind of standard definition of local Hamiltonian problem, people already know this is QMA complete, where QMA is a quantum version of MP. So this is the standard definition. Okay, so we have introduced a local Hamiltonian problem, and you will ask, okay, what's new in this talk? So in this talk, we will study a subclass of local Hamiltonian problem, which we call it as local Hamiltonian problem with succinct ground state. So similar to the standard definition, we again we're given local Hamiltonian and we wish to decide whether the energy is low or high. But in addition, in the yes instance, we assume the ground state has some kind of classical description. So what do I mean? So I mean we assume there exists a classical polynomial classical circuit which can compute the amplitude. Or in other words, we assume we have query access to the amplitude. Here I wish to emphasize like there in our setting there is no sample access. We only have query access. This makes a big difference. I mean intuitively because in total there are 2 to the n amplitudes. So if you can only query amplitude one by one, it's highly non-trivial to test the global property, like testing the ground energy. And one more remark I wish to say is like I think sample access and query access are incomparable. But we only assume query access. So this is our setting. And you may ask, okay, you can define everything as you want, but why do you study this problem? Like, what's the motivation? And where does those kinds of succinct assumption comes from? So the motivation of study this problem is to study some complexity implication of classical algorithms. So in particular, I mean, the succinct classical description, this kind of assumption comes from existing classical algorithms, where people use variational methods to estimate ground energy. And in those variational methods, they will use ansatz for ground states. And most of such ansatz are succinct. So for example, like there are two very famous algorithms in chemistry, which is DMRG and Hashicorp. Their ansatz are succinct. And also more recently, I think that many people try to use machine learning and neural network to estimate the ground energy. And their ansatz are also succinct. So this is where those kinds of assumption comes from. And the key problem, the key goal in this talk is to say what's the complexity implication. And in particular, I mean, in general, we know no Hamiltonian problem is QMA complete. So in this talk, we will try to understand if you, in addition, assume the ground state has some kind of succinct classical description, will this problem become classical, like MP or MA, or it will still be some kind of quantum flavor, like QMA? So this is the key question we want to answer. And our main result is to say, okay, this problem, yes, is classical. So we prove the local Hamiltonian problem with succinct ground state is MA complete. And here, MA is a randomized version of MP, where the verifier can use classical computation and randomness. And compared to the fact that general local Hamiltonian problem is QMA complete, our result is some kind of dequantizing result. So we dequantizing the verifier from quantum to classical. So this is our main result. And I think the most important thing to understand is whether this result is trivial or non-trivial. Like if it's non-trivial, why? So I will spend the rest of this talk to explain why this result is non-trivial. Why are two different aspects? One is technical reason and one is potential implication. So so let's explain this. So so let's begin with the technical reason why the MA result is non-trivial. So recall that we proved some kinds of dequantizing results. And as you may already notice, like the key factor which leads to such dequantization is because we assume we have succinct ground state. So if you try to reprove our main theorem by yourself, like you try to define a MA replication protocol, at first you might think this would be easy because I mean basically we try to design some classical verification algorithm. And by assumption, we already assume we have classical access to ground state. So at first you might think, yeah, it's natural to say you will utilize that classical query access and get a classical verification algorithm. But however, if you try this problem for 5 more minutes, you will quickly realize there is a technical difficulty. It's because there is no sample access. So why this makes a big difference? Because I mean, if you only have query access and you want to prove this inside MA, you are only able to query Hamiltonian and amplitude. But in total, there are 2 to the n amplitude. So basically, this means you need to get the global information of the ground state by by like looking at negligible fraction of the amplitude. So this is the first technical reason. But of course, you can further argue that, like, I mean, you see, the verifier also has randomness. So probably, although you can only query polling and amplitude, probably combined with randomness, like, yeah, you can do something more fancy, and you will be able to prove the MA result. I think this comment is fair, but personally, I think this result, the MA result, is even more non-trivial than just combining queries and randomness. Uh, Intuitively, this is because the local Hamiltonian problem suffers from the sign problem. And technically, I think normal randomized algorithm doesn't work. So for normal, I refer to like some direct discrete time Markov chain or something like uniformly sample the computation basis and the query the amplitude and do something fancy. So all the other methods tried, I didn't succeed. And finally, I choose the unusual method, which is based on continuous time Markov chain. And I think this is need to be unusual for computer scientists. So that's the technical reason I think this result is non-trivial. And a final remark here is I mentioned a sign problem, but I didn't explain what's sign problem. So feel free if you feel confused. I will explain this in the next few slides. So in summary, this is the technical reason. And so we explain like intuitively the technical reason is just because we have no sample access. And another perspective to say why the result is non-trivial is via some potential implication of dequantizing quantum advantage. And for quantum advantage here, I refer to a problem called local Hamiltonian problem with guided state. Informally speaking, this problem is related to a quantum algorithm for estimating ground energy. And this algorithm basically says, if in the beginning we magically get a guided state, then we can use quantum algorithm, like use phase estimation to get the ground energy. And here, the guided state is just some kind of good guess of the ground state. So this quantum algorithm basically says if in the beginning you can magically have a good guess of ground state, the quantum algorithm can help you to improve the guided state to ground state. So it's something like this. And this quantum algorithm is very popular and is one of the mainstream quantum algorithms for chemistry or condensed matter physics. And many people, including me, believe this algorithm might provide potential quantum advantage for chemistry. And this is one of the most promising applications of quantum computing. But on the other hand, I think we should always be very careful when we claim quantum advantage. And we should be careful, particularly for this algorithm based on guided states, because in this algorithm we make a very very like non-trivial assumption. So we assume in the beginning we have guided states, and most proposal says we can get guided states from existing classical algorithms. But as we mentioned before, like those guided states, those ansatz are always succinct. So basically, this means we assume we have classical access to guided states. So a natural problem would be, if you have classical access, can can you design classical algorithm? Like, do you really need a quantum algorithm? So this is the background. And if you study this problem in a complexity view, you will study a problem called local Hamiltonian problem with guided states, where in the yes instance you assume there exists a guided state, and the question would be, what's the complexity of this problem? It's still a quantum problem like QMA, or it will be a classical problem like MP or MA. So for this standard definition of local Hamiltonian problem with guided states, people already give a very elegant answer to say, no, you cannot. So this problem is indeed quantum, and you cannot dequantize it unless QCMA equals MA, which is unlikely to be true. So this is what people know before. Um, and uh, and okay, so anyway, in summary, we have introduced what is local Hamiltonian problem with guided states. And you will ask, okay, fine, you can do everything you like, but what's the relationship between this problem and the problem you are working on? So I say like so previously we said for the standard definition of guided states, this problem cannot be dequantized because it's QCMA complete. And our result in fact is related to a further question. It's like uh, if the guided states we have are stronger than the standard definition of guided states, can it be dequantized? And for stronger guided states, here I refer to two different definitions. So one is succinct ground state, which can be interpreted as a extremely strong guided state, because it's exactly the ground state. And another one is called strong guided states, which lies in between the standard guided states and the succinct ground states. And there's no standard definition of strong guided states, but for some reason, here I temporarily define it as a state which has entry-wise 1 over Pauli overlap with the ground state. So this is two definitions of stronger guided states. Um, and so you may ask, okay, so what's the relationship? So if you still remember, in the beginning I mentioned like the difficulty for dequantizing is because of the Simon problem. And the key information I wish to give in this slide is extremely strong guided states can help you to circumvent the Simon problem. So what do I mean? So for the sign here, I refer to a concept called stochastic. So stochastic Hamiltonian is a subclass of general Hamiltonian, which is known to be sign-free. So basically, this just means like there is a natural way to connect stochastic Hamiltonian to a Markov chain. So there are natural ways to design a randomized algorithm for stochastic Hamiltonian. And I mentioned, like I say, the difficulties for dequantizing is because of sign problem. Uh, this is because if we know the Hamiltonian is sign-free, even before our result, we already know we can dequantizing it. So we know the stochastic Hamiltonian, even with strong Getty states, is MA complete. And previously, the open question is like, can we circumvent the sign problem? Like generalize those kinds of quantizing results from stochastic Hamiltonian to general Hamiltonian. So our results shows for the extremely strong Getty state, yes, we can. Like even for general Hamiltonian, we can prove MA complete. Like we can dequantizing the complexity class from QMA to MA. And one open problem is whether you can circumvent the sign problem also for the strong Getty state one, and whether you can again use some kinds of continuous Markov chain, which might be underestimated, to generalize the results from stochastic Hamiltonian to general Hamiltonian. And so this is the open question, and this is the relationship between our results and the dequantizing problem. And one more remark I wish to give is so the Monte Carlo methods used in our current paper is very sensitive errors. So there are many people ask me how do I even expect to generalize this method to the strong Getty state one? So the reason I believe the conjecture, the open problem is true, is because I know there are more robust Monte Carlo methods which can handle the errors. So in particular, like the Monte Carlo method in the Bravi 14 paper is more robust, and if you try to prove the open problem, you might need to read this one. So yeah, so this is the motivation. Sorry, this is the relationship between our problem and the quantizing problem. And so finally, I wish to give a sketch or our proof. So like recall what we want to do. So we want to prove for general Hamiltonian, you can define a MA verification protocol. And the start point is like we know for stochastic Hamiltonian, you can use the discrete time Markov chain to design the MA verification protocol. So the first step would be try to connect the general Hamiltonian to stochastic Hamiltonian. So this technique is called the fixed node Hamiltonian, which comes from a very old chemistry paper. But this method is well known, like for many years. But however, directly doing this doesn't work because if you use a discrete time Markov chain, you will meet a problem like the norm of the new Hamiltonian will be extremely large. So to circumvent this problem, we use a very special Markov chain, which is a continuous time Markov chain, and this paper is very new. And we also add some, in addition, we add some consistent checks in this Markov chain to get a MA verification protocol. And in fact, the most important thing I want to say here, so is I wish to mention what's the key difference between the continuous time Markov chain and the discrete time Markov chain. So the continuous time Markov chain is based on something called Getty-Skas algorithm, which use varying step size. So then the performance will be average performance. So what do I mean? So imagine you are doing a random work on some, for example, 2D plane. So this algorithm will take different step size for different points. So the average runtime will depend on the average performance. Compared to the discrete time chain, which takes a fixed step size. So the discrete time chain will depend on the worst case performance. So I think that's a key difference, makes the continuous time chain different from the discrete time chain. And another remark I wish to make is like our setting is different from like the Bravi paper is different from like Monte Carlo or like quantum Monte Carlo methods. So we have different tasks and we have different settings. So we need different conditions. So in particular, we don't need spatial gap because we are not in a sampling. Instead, we use the promise gap. So that's a final remark. And in summary, finally, like a summary is like we show that extremely strong guided states can help you solve the same problem. And the open question is like, can you do something similar for strong guided states? And also another open question is like, I personally find the continuous time Markov chain very magic, and probably I can be used to somewhere else. And also, and finally, also I think, although the local Hamiltonian problem with guided states, the algorithm is very good, but I guess it's always good to design some new algorithm. For example, you might design quantum metropolis algorithm, something like this. Okay, so that's all. Thank you. Any questions?
All right. Thank you very much, Jiang, for that very nice talk. Any questions? Oh, yeah. Please step up to the mic.
My question is really quick. Can you just redefine, is the entry-wise overlap with the ground state for the strong guided states? Can you clarify what you mean by that? I just didn't fully understand that.
So I just mean like the I mean for amplitude, like if you I mean so the amplitude of strong guided states divides the amplitude of the real ground state. It should be a real value and a positive value, which in between 0 and 1 over point.
Okay.
Yeah, so it's stronger than the standard definition.
I wanted to ask if this extremely strong guided state, how can you replace it potentially with something like just access to a state with low energy, not necessarily exactly the ground state,
Low energy.
like lower than the threshold for no instances?
So I think currently my approach cannot, because it's very different. So I realize it's very different to test the ground energy and test other eigenstates.
Thank you.
So that's very different. Like I think if you can test the eigenstates for any value of arbitrary eigenstates, I feel you will be able to you will break some complexity result.
Thank you.
Yeah, thank you.
Hi, I wanted to ask, so both for your succinct guided states and for these strong guided states, these are basis dependent properties, right?
Yeah.
Okay, and any comment on that, like how natural it is? What if I am interested in an assumption in a different basis?
Yes, I think that's a very good question. Like I so I don't have a very good answer. So one thing I want to mention is like I think even for stochastic Hamiltonian, people consider people had some like results related to this problem, because stochastic is also a notion which is base dependent. So I think they prove some from a complexity view, they prove finding a right basis is hard. Yeah, but I mean if you have more you have more conditions and you know much more for the Hamiltonian, yeah, I think probably you can do something new.
Okay, thank you.
Any other questions? One more.
I wanted to ask what happens when you replace this succinct description to classical sampleability, or so because you said you're explicitly not considering that. Does it become trivial, or is it just a different setup?
So so first I think sample access will some condition sample access with some other condition will make this problem trivial. Yeah, but for sample access itself, I'm not very
Oh,
sure.
I see. Okay.
Yeah.
Thanks.
So yeah. Thanks.
Other questions? All right. If not, let's thank Jiaqing again.